So let's look at an example where a soft policy is indeed needed. That is, with a hard policy, you won't be able to get the optimal performance for this specific MDP. So we have a simple grid environment that is shown there, right here, with 3 states and 1 terminal state. In each state, you can either perform a left or right action. The reward is -1 per step. So we would like to get to the goal. I mean, the optimal policy gets to the goal as soon as possible in expectancy. Taking the left action always goes left and the right action always goes right, except for the middle cell. In the middle cell, in the middle state, these are reversed. So left will take you right and right will take you left. The issue is that the states are identical from the policy perspective. So the policy will be exactly the same for each one of the cells, right? So for each state, you have to give the same. The policy is unaware of which state we are exactly in. The best policy in this case, by the way, what would be the best deterministic policy in this case?
Just going right towards the goal.
So there's no best, right? So with a deterministic policy in this case, you'll never be able to reach the goal. Right? I mean, yeah, you can start at state S, go right, and then if you perform the same action right again, you'll get to state S. You just go back and forth between state S and the middle state, right? So a deterministic policy in this case will not be able to, you'll get an expected reward of -infinity. You'll never be able to complete the game. But there is a very specific optimal soft policy in this case, which is go left with probability 0.41 and go right with probability 0.59. Okay, so this is just an example, and you can see here the policy space on the right. It shows the policy space because it provides the probability. The x-axis is the probability of taking the right action, and of course, it's just a one-dimensional policy because this defines specifically also the probability of taking the left action. It's just 2 actions. And the y-axis would be the expected sum of discounted reward, because we want to be as high as possible on that front. And indeed, it shows you the expected sum of expected rewards for each one of these policies. Right, this is the entire policy space here on the x-axis, and you can see that the best policy, the optimal stochastic policy, is somewhere around here, the optimal soft policy. The stochastic policy and soft policy is the same thing for our purposes. Oh, I use these interchangeably, okay? So not to get confused. They do mean the same thing here. And of course, this can also be more effective than than a specific epsilon greedy policy, right? So if you're trying to do Q-learning with an epsilon greedy policy, Q-learning will eventually converge on some epsilon greedy policy, for instance, either with the hard max action of going left or hard max action of going right, but if you use a specific epsilon, then you will converge on, in this case, some suboptimal policy, right, as demonstrated here. With an epsilon of 0.1, either converging on a hard max of going right or a hard max of going left. Next, let's try to actually define our policy gradient and solve. Okay, later on I'm going to show you some results for this specific domain using a policy gradient algorithm. And I mean, I'm going to show you the learning curve, but before that, we're going to derive the policy gradient theorem and the reinforced algorithm. It's the simple algorithm that uses the policy gradient theorem, a policy gradient. Okay, so the main problem that we're trying to solve is estimating the gradient in J, the policy gradient, right? J, the expected sum of discounted reward for any given policy, Well, it depends on both the action selection, right? Which action do we select in each one of the states, but also on the distribution of states in which those selections are made in. So the states that we're going to see when we follow the specific policy. So both of these probabilities are affected by the policy parameters, right? By the specific policy that we're defining. So it might seem that it seems, I don't know if impossible, but very hard to solve or to approximate without knowing. I mean, to solve it's probably impossible, but it also seems to be very difficult to approximate without knowing the transition function or the distribution of visited state, right? So we need to know what's the probability of arriving at any next state given a current state and the action that we take. However, we will not assume to know that. We are staying with the reinforcement learning assumptions, and we don't assume to know the model, the exact model that we are working under, of the space that we are working in. The policy gradient theorem allows us to evaluate the gradient in J without the need to know the model, the transition model. So let's derive the policy gradient theorem.